And welcome back to our last episode in the series of representing data. Last episode was about run length encoding, which is the first part of this success criteria. We're now going to do about Huffman coding for the last part of this lesson, last part of this section. Huffman coding is very good for compressing data of text. It's called variable length compression, where letters which are used more frequently are stored in less bits than letters which aren't used frequently at all. For example, if A might normally be used in 1 bit, whereas the letter Z might be used in 3 bits or 4 bits because it's not used that often. That's how you get to this variable length compression. It doesn't really care about the order of the data, just the frequency of that. So how many times is the letter A in a particular string, rather than where the letter A is in that string. And like I said, the most frequent items are given the shortest amount of bits, the shortest codes, because it keeps the compression down. Useful in text. So E is going to be used a lot, whereas Z will be rarely used. And like I said, Z would use many more bits than, say, a much more frequently recurring letter like a vowel would. Let's do an example here. Bookkeeper. We're going to create a Huffman tree, which is where every node, a rounded rectangle in this case, stores the frequency of that particular value. And if there's a letter in there, we'll also have a letter. Let's break this down a bit. First of all, find the frequency which each of those letters is. So we know there's one B in that string, there's one P, there's one R, there's 2 O's, 2 K's, 3 E's. Then what you do is you arrange those in the order, the smallest at the top, by frequency. So 1B, 1P, 1R. Now there's a little bit of debate here whether to do this where it comes in the string, whether it's alphabetical. It's up to you how you do that. Normally, when you're in the GCSE, they give you the actual tree to follow. You won't need to worry about that. Then what you do is you look at the top 2 nodes and you combine those together. So in this case here we have 1B and 1P. We would combine those over to say that there's a frequency of 2, no letter, but that 2 is made up of 1B as one node and 1P. Then what you do is go back to step 1 again and arrange them back in order, the smallest at the top. And then you'd have the 1R now would be at the top, followed by a 2, which is made up of 1B and 1P, followed by 2O, 2K, 3E. You then combine the top 2 and keep on doing that till eventually you only have 1 node left on the left-hand side. It's probably hard to visualize without actually seeing it, so here you are. We put these in order, right? 1B, 1P, 1R, 2 O's, 2 K's, 3 E's. We're going to look at these first 2 and combine them. And that's what we did here. 2 was 1B and 1P, that's what 2 was made up of. Then put them in frequency order again with the smallest at the top. So that 1R where it was here has now gone up to the top because that's the smallest frequency. Then there was the 2 that we combined, and then the 2O, 2K, 23. Now what we're doing again is we're looking at the top 2. So we can see that 1R and a 2 will give you a 3, which will be made up of 1R and the 2. And that's what that looks like. There's the 3, made up of 1R, and then the 2, which was made up of 1B, 1P. So this 2 here has gone to here, and that 1R, and that's what we've done. Then we reorder the frequency, so we had a 3, which means then the 2O and the 2K are up there, and the 3 we can keep there where it is. What we do, we look at the top 2, and we combine them again. So we're now going to have a 4 with 2O and 2K off it. Then reorder by frequency, so we've got the 3, the 3E, and the 4. We're going to combine the top 2, so this is going to give you a 6, which is made up of this branch and then this branch, and that's what that looks like. The 6 made up of that branch, the 3 with a 1R, the 2, and that's where that bit is there, and also the 3E, which is here. And then we've put them in frequency order again and combine these 2 again to give you a 10, made up of all of those. You need to be able to encode these, so once you've got your final Huffman tree, you then have to label it the 1s and 0s. Some people say left has to be a 1, some people say the left has to be a 0. It doesn't really matter as long as you keep to the same convention all the way through your Huffman. So if you've gone here with 1 on this branch and then a 0, this top branch always has to be a 1 and a 1. So that's a 1, that means that's a 0. Go to the next branch. If this top one here is a 1, that bottom one's got to be a 0. Go to the next branch, that 1 and that 0. Next branch is a 1 and a 0. Next branch is a 1 and a 0. Why have we done that? Well, because we can now encode each of these letters. The B, well, how do we get to the B? Look, it's all the way down there. How do we get to that B? What's the route we take? So start from the left-hand side. Let's get to the B. So we have to go down this branch here, 0. That gets us to here. Then we can't go down there because that's going to be a dead end. So it's 0, then a 1. That takes us up to here. Then we can't go to that because that's going to be another dead end. So it has to be 0 to get to the 6, 1 to get to the 3. Follow the 0 branch to get to the 2. We're trying to get to the B. So then we got to the 1 here. So we went 0, 1, 0, 1. And that's what B is, 0, 1, 0, 1. How do we get to the P? 0, 1, 0, 0. How do we get to the R? Here it is here. 0, 1, 1. How do you get to the O? Where's the O? Here. 1, 1. How do you get to the K? What's here? 1, 0. And how do you get to the E? Where's the E? Here. 0, 0. And now you've encoded all that. So if you were now to write the string bookkeeper back out again, using the code you've got, it would be 0101, 11, 11, and just put them all in, fill them all in like that. So the final binary number for bookkeeper would be this. So that would take 25 bits to store. Now imagine we weren't using Huffman, trying to do this in our own way of storing these characters, not using ASCII then, because remember it would be 10 characters here for ASCII, which takes 7 bits, would take us 70 bits. We're going to try and do it even simpler. We know that there are 6 different letters there, 6 different values. How many bits would we need to store 6 values? Well, 1 bit would store 2 values, 0 or 1. 2 bits would store 4 values, for example 00, 01, 1011. 3 bits would allow us to store 8 values, so that's how many we'd need. We'd need 3 bits to store each of these characters. There are 10 characters, so it's 3 times 10 would take us 30 bits. So without using Huffman, which would take 25 bits, it takes 30 bits. So that's a compression then of 16%, 5 over 30. Because we had 30 characters and we managed to do it in 25, that means we've saved 5 characters, we've compressed it by 16%. And just while we're on about trying to work out the minimum number of bits to store the number of characters you have in an uncompressed string, what you could do is just count the number of unique characters in that string. In this case, it was 6. Take away 1 and then convert that to binary, and how many bits does it take you to convert that to binary? So in the bookkeeper one, there are 6 different characters. So we take away 1, that leaves us 5. What's 5 in binary? 101. That's 3 bits. So it would take the minimum number of bits would be 3. That's just really a way of thinking about it that way. Now, it's a big old worksheet for you to try now. Steps you through bit by bit to start off with. I'd like you to have a go at that. And then we will go through the worksheet in a moment. Pause the video, have a good go at that. Welcome back. This is Huffman coding worksheet. We're going to go through the answers here. You're going to use pull as an example that's given to you all the time and use potten for the answers you're going to give. Just remember the step ahead gave the answers to the previous step just so you don't fall too far behind. But let's just show the answers to that as well. Okay, so potten. There's 1 P, there's 1 N in there, there's 2 O's, and then there's 2 T's. There's your answer. Step 2 was to create the nodes in ascending order for that. So 1 P, 1 N, 2 O's, 2 T's. And what's the next step is step 3, where you combine the top 2 nodes together. So if we look at these, they're 1 P and 1 N, so we put 2, which is made up of 1 P, which I haven't answered here, 1 P, followed by 1 N, and it's a little p, let's get it right, case is important. Then, what's that? The 2 O's here. We combine those, and that should be the 2 T underneath, and so that's back in order. Step 4 is to reorder those again, which we just done. And then step 5 is to combine the top 2 nodes. The 2O and the 2 are going to go together to make a 4. Here's the example for pull, but we're going to do it on this one here. There's the 4. And then we then combine these again to get a 6, which gives us the 2t and the 4. And that's it. We've got one node left over. So remember what we're doing. Each time we're going through the top nodes. So we put them in order, take the top 2, combine them. So that is a 2, which is made up of 1p and 1n, and then 2o, 2t. Then we can combine these again once they're ordered. So 4, which is made up of this branch is here, and the 2o, which is there, the 2o. Then the 2t was still left, remember, here. Reorder, then combine. So this is going to give you a 6, which is made up of a 2t, and then this branch. The 6, we're going to have 2t and this branch. Final step is to label everything. So if you know this is the 1s, then that's the 0s. That means the top branch is the 1, the bottom is the 0. Top branch is the 1, the bottom is the 0. Step 7 was to then find your way through these. So the P was 011. Where's the P? Here. So the P starts here. So it's 0, 1, 1. I should say 0, 1, 1. The O. Well, there's the O here. That's a 0 followed by a 0. The T is right there. So it's a 1. And then the N down here is a 0 followed by a 1 followed by a 0. And that gives you the answer there. Then write out the string pattern and replace every single one of those with the actual codes here. That gets you 0, 1, 1, 0, 0, 1, 1, 0, 0, 0, 1, 0. Now, here is some examples from previous papers. Here's a Huffman tree. It just started you off with a 0. First thing you want to do then is just label the rest of the branches, put a 1 here. So that means the left-hand branch is 0. So left hand 0 means the right is 1. Left hand is 0, right must be 1. Left hand is 0, 1, 0, 1, 0, 1. Put them all down. And it's saying here, part of our all-stars real was incorrectly encoded, as in figure 2 below. What string does this encoding represent? Now, the trick on this is that if you can't go any further, that tells you what letter you're at. So look, we have 4 1s to start off with. Well, let's do that. 4 1s. 1, 1, 1, but there's nowhere else to go, so we can only use 3 of those 1s, and we have L. So we put an L here. Let's use 3 of these 1s, and then it's 1 and 3 zeros. 1, 0, and 0. There isn't one, so we're going to use 2 of those, and it's an E. So now I've used 1 and the 1 and 2 zeros. So now we're here, 0, 0, 1, 0. 0, 0. We can't go any further, so it's an A. So where we are, we're at 0, 0. Now we're at 101. 101. Oops, we can still go further. So it's 1010. 1010. So it's an S. 1010. That leaves us 1011. 1011 T. So L-E-A-S-T, least. The second part, write down the correct encoding for star. Okay, well, where's the F? Here, star. 1, 0, 1, 0 gets us to S. And the star bit, the T, 1, 0, 1, 1. Then the A here, 0, 0, and then the R, 0, 1. So you'd put all that down in binary together there. Another question here, this Huffman tree here, the clue in this one, it says A is binary code 0, so A you'd have to label as 0. That means then the left hand branch is 0 and the right is 1. So left 0, right 1, left 0, right 1. There's a string right here. Okay, so what we have to do here, first of all, follow the code. So G, what's the code for G? Here's G, 1, 0, 1, 0, and then S and H. S is 1, 1, 0, and H is 1, 1, 1. 1, 1, 0, 1, 1, 1. And it says here, the string shown in figure 5 could be encoded using ASCII. ASCII uses 7 bits to represent each character. How many bits are saved using Huffman coding rather than ASCII to represent? Well, using ASCII by itself, there are 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. So it's going to use 13 times 7 bits. How much would Huffman use? So you can just write out this string and then each of the codes. So A is 0, is that right? A is 0. So wherever you see an A, just write down a 0. 0, 0, 0, 0, 0. Where you see a G, it's 1 zeros. So there's 1 0. And all you do is just fill in the blanks all along. That'll get you that binary number. Add them all up, and that's 25 bits. So if we knew it was 7 times 13 to get you 91 bits for ASCII, but this is only using 25, well, 91 minus 25 means you've actually saved yourself 66 bits, and that's your answer. Last question here is to construct a Huffman tree. If you're on the new spec, you won't need to do these, you only have to follow them. But if you're on the old spec, you still have to construct these trees. What would you do? Well, first of all, put these in frequency order with the smallest at the top. So U6 would be at the top, followed by I14, O15, A16, E24, and then just group the top two, reorder, group the top two, reorder, group the top two, reorder, until you've only got one node left. That's what you end up with. Let's do the first one for you. U6, and underneath it would have been I14, so you'd have grouped those two and would have got 20, which would have made up of U6 and I14. Look, that's there. 20 was made up of 6U, 14I, or U6, 14. Then you would have redone those again, the 20, which would have been 15, the 16, the 20 you'd made, and the 24E. And then you just keep on grouping, and that's what you end up with. This. Right, replay this video a few times, you didn't quite understand what was going on there. So final part of the lesson, run length encoding versus Huffman. When would you use either? Well, it just depends on what's the scenario, what are you going to do, what do you want to do? Is it images? Is it text? Is there lots of colours? Are there lots of repeating colours? Are there lots of repeating text? The general rule though is run length encoding for images, especially if they've got repeating blocks of colour, and Huffman for text. So here's a little table to sum that up. Run length encoding works well on images that have blocks of the same colour, and text that has repeating symbols. Huffman is very good at compressing text. Run length encoding isn't good for written English because there's just not enough repeating patterns. Problem with Huffman is you have to keep making the trees for every single string that's compressed, which can be a bit inefficient sometimes. Let's see what you understood from this particular topic. Head yourself to Edmodo, go to the quiz representing data, Huffman coding, have a go at that. Summarize then, how do we compress using Huffman coding? You should be able to do that. You should be able to interpret Huffman trees. You should be able to follow them. You should be able to create your own. On the new spec, you won't need to do that, but on the old spec, you will need to do following and creating. And also, you should be able to work out the number of bits that are required to compress things in Huffman coding. So let's summarize this whole topic. We humans, we process analog, it's continuous. We're developed that way, but computers can't. They've got to listen to it at certain times, take a reading, and store it as binary data. Everything has to be converted to binary to be able to be stored on a computer. Using my number system series and this system series, you should now know about the different numbering systems. You need to know about decimal or denary, which is base 10, binary, which is base 2, and hexadecimal, which is base 16. You need to know about binary shifts, being able to shifting from the left and to the right. Moving to the left increases the number by a factor of 2. Moving to the right decreases it by a factor of 2, or halves it. Even letters need to be stored as binary numbers. Those are character sets. Images are made up of pixels. The amount of data you store in each pixel is the color depth. If you increase the number of pixels or the color depth, then the file size will increase and so will the quality. But then the opposite will happen if you reduce the number of pixels or the color depth. Sound is sampled at set times, called a sampling rate. Every time you sample, the information that you record, the amount of bits you allow for that is the sample resolution. The better the sample rate and resolution, the bigger the file size, but better quality the sound, more accurate it is to the original. Compression, files can be compressed. We use that to save storage space, to make it easier to transmit. There were two types of compression, lossy and lossless, and you were showing two different kinds of compression algorithms, run length encoding and Huffman trees, which was this lesson. Hey, here's some exam style questions to have a go at. Pause it and we'll come back with the answers in a little bit. Welcome back. First one, convert the binary number 1011001 into decimal, show you working. Put it into its number columns. The rightmost column will be the ones, the next column will be double that, which will be the twos, the next column, the third column, will be the fours, as you get the mouse pointer out. Ones, then the twos, the fours, the eights, the 16s, the 32s, the 64s, and the 128s. So you know there's 128, no 64s, 132, 116, 11, add it all up, you get 177. Convert 1011001 into hexadecimal. Well, group it into nibbles, or groups of 4 bits. Then convert those, so 1011 is 11, and 001 is 1. Remember, you're not allowed double digits, so 11 in hexadecimal is B, so the answer there would be B1. Question 3, convert that binary string into a 4x4 image, so take it into groups of 4. 1, 2, 3, 4, so your first row will be 0110. Doesn't tell us what's what, so let's make the 1s black and the O's white. So it'll go white, black, black, white. Next row will be black, white, white, black. And following it along like that, you're going to get this idea. Or you might have the opposite. You might have this as black, white, white, black. Question number 4. If M is represented as the code 011010, and then what would be P? Well, P is M, N, O, P, so that's 3 along the alphabet. So what you could do is convert M to denary, add 3 to it, and then convert that back to binary. Or what I've done, just as a form of revision, is I'm going to keep it as 01001101, but I'm going to add 3 to it. Now 3 in binary, remember, is 1, 1, which is 1, 2, and 1, 1. Just use binary addition. A 1 and a 1 is 0 carry 1, which means it's a 1 and a 1 again, which is 0 carry 1, which is again another 1 and a 1, which is 0 carry 1, which is again another 1 and a 1, which is 0 carry 1, and then there's a 0 here, so it's a 1. And then that's nothing, and that's nothing, so it's 0, 1, 0. So just adding that little test, you could have gone to 77, added 3 onto it to make it 80, and then convert back to binary, which would have got you that binary number. Question number 5. Calculate the size of a 10-second sound clip with a sampling rate of 150 and a resolution of 8 bits. Give your answer in bytes, not bits. So remember, it was length of the clip multiplied by the sampling rate multiplied by the sampling resolution. 10 times 150 divided by 8, and then we turn it into bytes. So to go from bits to bytes is divide by 8. But I'm just going to do it right there. So 8 divided by 8 is 1, so it's just 10 times 150, which is 1500 bytes. Question 6 there is, what method of compression would be most appropriate for compressing a book? Explain your answer. I would say it would be Huffman. The reason being is a book has lots of non-repeating patterns, so run length encoding wouldn't be very good. So we'd really want to use something like Huffman coding to do it that way. Be a big old tree. Question 7. Explain 2 ways in which the quality of the playback of a sound file can be improved. Well, the more times we listen to that sound, the better quality it will be, because the more accurate it will be to that sound, because it will follow the waveform a bit more precisely. And also, every time we sample it, if we have a higher sampling resolution, then there's more that can be measured at that point in time. So the two ways in which the quality of the playback of a sound file can be improved is improve the sampling rate, sample more often, increase the sampling resolution, allow more bits to make the measurements. And 8, again, if you're on the new spec, you won't need to create Huffman trees, just follow them. Create a Huffman tree for the string small. So first of all, work out the frequencies of these letters. There's one S, one M, one A, two L's. Put them in frequency order from the smallest at the top right down to the highest frequency at the bottom, which we've done here, it's just in a line here. Then what you want to do is combine the top two nodes and then reorder. So let's combine the top two nodes, which would be the S1 and the M1, and then that would be here. So there's that, S1 and M1 combined is 2. Reorder, so the A now, the A1 is at the top with the L2 down here. Combine these two again, so that's going to get you a 3, which is made up of this branch and then the A1. Looks like that. Reorder, the 3 is going to be at the bottom, the L2 is going to come up to the top, which is here. Combine these two nodes again, so you can have a 5, which is made up of an L2 and then this 3 branch, which looks like that. And then you've got the 1 node. If you need to go any further, you then start labeling these, for example, 1, 0, 1, 0, 1, 0, and then write the string out again. But there's no need for it in this. It hasn't asked you to do that. Now, that leaves you the end of topic assessment. No redos on that one. Just one go at it, and there's 2 quizzes to do. You'll need to use the graphic that comes with it for the pixel questions and the run length encoding questions. So make sure you've got the graphic that comes with that, the image. Have a go. Good luck. That's the end of this series. Cheers.